Every week, logistics companies like TNT Express coordinate the movement of over 4 million packages across fleets of aircraft and tens of thousands of trucks. These operations are remarkably dense. The math governing this movement has massive financial and environmental consequences. By redesigning their Italian routing network, TNT saved €207 million and cut carbon dioxide emissions by 283 million kilograms. Networks of this size contain billions of possible routing combinations. A human dispatcher, relying on intuition, cannot manually determine the most efficient path. To solve logistics at scale, physical infrastructure is translated into mathematics. These are network models. In these models, nodes represent physical locations, like warehouses or cities. Arcs are the available routes connecting them. Peak efficiency relies on translating the physical rules of the road into a strict system of linear programming. The most basic logistical puzzle is the transportation model, where goods travel directly from a source to a final destination. The objective function is to minimize total cost. The model calculates this by summing all the shipping costs multiplied by the specific quantities of goods sent down each route. To solve this, we define a core decision variable, Xij. This represents the exact number of units shipped from source I to destination J. We encode the factory's physical limits into the math through supply constraints, ensuring the model cannot distribute more units than a specific source actually produces. Customer requirements are locked in as demand constraints. The math is forced to deliver exactly what is needed at the destination node. This mathematical structure is highly adaptable. To test a potential new facility location, an analyst adds a source node, inputs the estimated costs, and reruns the equations to check the impact on total network costs. This baseline linear program acts as a precise balancing engine. It weighs every factory's maximum output against every customer's requirement to find the cheapest possible distribution. In the real world, goods often pass through regional distribution centers rather than traveling direct. We adapt to this by using a transshipment model, which introduces intermediate nodes into the middle of the network architecture. A distribution center maintains no inventory of its own. It receives goods and passes them to the next stage. Look at this linear programming matrix. To model this behavior, we introduce a mathematical rule called conservation of flow, setting the right-hand side of the intermediate constraints to 0. We translate conservation of flow into an equation by stating that the total flow into an intermediate node minus the total flow out must equal 0. The matrix enforces this by pairing positive and negative coefficients. By adding this zero-sum constraint row, the linear programming engine becomes capable of routing goods through elaborate, multi-stop global supply chains. Linear programming isn't limited to moving bulk freight. It can be used to make specific logical choices, like matching workers with tasks. This is the assignment problem. A pool of resources must be matched one-to-one with a pool of tasks, accounting for varying costs or skill levels. The network architecture adapts to this by restricting the supply and demand at every single node to exactly 1. Each worker represents 1 unit. Each job requires 1 unit. The decision variable Xij shifts from a continuous quantity to a binary integer. This shipments table illustrates the result. The variables resolve into binary logic, 1 or 0. A 1 means a worker is selected for a project, and a blank cell means the path is ignored. This binary logic solves the shortest route problem. Finding the fastest path through a city grid is achieved by forcing a single binary unit of flow from a starting node to a destination. This binary logic shifts linear programming from a tool for calculating volume into a system for making specific yes or no selections. While linear programming can be configured to solve nearly any network, calculating massive matrices isn't always the most efficient approach. Consider the minimal spanning tree problem. This is a geometric challenge used to connect all nodes in a network with the minimum total distance, like wiring houses to a utility grid. Instead of a heavy linear program, analysts use a specialized greedy algorithm designed specifically for this structural geometry. Notice this cluster of 8 unconnected nodes. The algorithm executes a simple opening move. It selects any starting node, identifies the shortest available distance, and links it to the closest neighbor. The algorithm loops through the currently connected pool, links the closest unconnected node, and repeats until the entire grid is linked. Recognizing a network's specific geometric behavior allows analysts to bypass heavy matrices and deploy algorithmic shortcuts that resolve in a fraction of the time. In the early 2000s, the Cuban sugarcane industry applied these mathematical theories to a massive logistical crisis. The puzzle required timing the movement of raw cane from dispersed agricultural fields through intermediary storage facilities and into final processing mills. Modeling this reality required over 40,000 decision variables, tightly bound by 10,000 interlocking constraints. Once correctly formulated, modern solvers process these tens of thousands of constraints in milliseconds. Vast logistical systems, whether trucks, snowblowers, or sugarcane, yield predictable outcomes once the variables are correctly constrained. Architecting a precise mathematical model achieves a level of global efficiency that manual human oversight simply cannot replicate.